Okay, so we're now going to move on to electric potentials and show how we can come up with a sensible way to write down what an electric potential is. So in order to do this, we're going to need to make use of Stokes' theorem, which hopefully you remember from mathematics. So what Stokes' theorem tells us is that if we consider an integral around a closed path, so here we've got a closed path, so this left-hand side is referring to the integral around this line, around the boundary of our path, and that is equal to the curl of f through the surface, and this is the normal to the surface here. So that's going to be perpendicular to that surface there. So that'll be the direction of the normal there. So it's telling us that the integral around the boundary of that path is equal to this integral here over the surface of this same surface here. So this has to be the boundary around this surface here. So how we can make use of that is if we remember what we've just shown, that the curl of an electric field is equal to 0. So del cross E for any electric field is equal to 0. And this means that we can put this 0 into this part of the equation when we replace our field F with our electric field in this case here. So this thing here, if this thing in here is 0, then this whole right-hand side has to be 0. So this tells us that the integral around a closed path of E dot, let's call it dl in this case, is equal to 0. And now this is important because it means that whenever we go around this path, things are going to add up and subtract off so that around the total path, we end up with 0. And the consequence of this is if we consider 2 points on the path, say A here and B over here, it doesn't matter how we get from A to B. We could go that way, we could go this way, we could go some other way. However we get from A to B, we must have the same number. So getting from A to B is independent of path. And that's true because however we get back, we're still going to be 0. So if we go this way and then back along the same path, that's 0. But we could also go this way and then back along this way, and that also has to be 0. So that means that this thing must have been the negative of that thing. So this implies that getting from A to B is independent of path. Which, I mean, we'd expect because we've discussed previously how the electrostatic force is a conservative force, and that's what a conservative force means. It means that it's independent of the path. So this lets us write down an expression for a useful function, which we'll end up calling the potential. But we've got V of R is equal to minus the integral from our origin, whatever we're defining our origin as, to some point R. So it's important that this point and this point are the same, of E dot dl. And this has a unique number because it doesn't depend upon that path. Okay, so let's take this expression and think about how we can use it and why it's kind of useful to do so. So with this, we can write V of B minus V of A. So we're considering now going from A to B like we were up in that figure. According to this definition, this is equal to minus the integral from 0 2b of E dot dl minus, so plus the integral from 0 to a of E dot dl. Now, what we can do is we can keep this first one as the same, and I'm going to switch the limits on the second one. So now we will go from a to 0. So this is going in the opposite direction. So that's changed my sign of E dot dl. So now you can see that because we've got the same terms in these two integrals, we can combine this and write this as negative now from a to b, because we're going from a to 0, 0 to b. So that's from a to b of E dot dl. So this is our expression for the electric potential between 2 points A and B. Now, it's useful just to think back to our fundamental theorem of calculus. Hopefully, so this is the fundamental theorem of calculus. You would have seen when you were learning about this that if we take the difference between two functions, the function at b minus the function at a, then this is equal to the integral of f dash x dx, or we can write this if we want as the integral of df dx, and this is going from a to b. This is from a to b. So that is when you were first learning about what integrals actually were, how you went about defining them. So this is basically saying that the derivative is undoing the integral there. And this applies in all three dimensions, the y and the z direction as well. So we can write this in 3 dimensions as VB minus V of A is equal to the integral from A to B of, rather than writing df dx here, we write the grad of V, and this is dotted with dl. So this is just the 3-dimensional version of our fundamental theorem of calculus. And why that is important is we've got VB minus VA here and VB minus VA here. So this is saying that this thing here must be equal to this thing here because they're both equal to VB minus VA. So let's just write that out. We've got that minus the integral from a to b of E dot dl is equal to the integral from a to b of grad V dot dl. And then because we've got the same limits here and both these are dotted with dl, you can see that this thing is going to have to be the same as this thing. Well, with our negative, we'll have to put our negative in there as well. So we can say this tells us that negative E is equal to grad V, or that E is equal to minus grad V. And so this V is actually how we define the electric potential. So the electric field is the gradient of this scalar product here. So the electric field can be written as the gradient of a scalar product. And we call that scalar product the electric potential. So this is the electric potential. And we'll see an example, and then we'll go on and look at why this is actually useful. Okay, so let's put this into practice by solving a problem. So this is problem 2.20 from Griffiths. in this question it says one of these is an impossible electrostatic field. Which one? So let's start with that part. We know that for an electrostatic field, the curl of the electrostatic field has to be 0. So what we're going to do is calculate the curl of both of these so-called electric fields and see that they satisfy that condition. So let's do A. The curl of E in this case is equal to K, and then we need to find the determinant of X, Y, Z, and d dx, d dy, d dz. And we've got xy, we've got 2yz, and then 3xz. So finding the determinant of this, we've got k out the front, and now in the x direction, we've got d dy of 3xz, so that's 0, minus d dz of 2yz, and so that is equal to 2y. And then in the y direction, we do d dz of xy, so that is 0, minus d dx of 3xz, so that is minus 3z. And then in the z direction, we've got d dx of 2yz, so that's 0, minus d dy of xy, so that is x. So you can see this is definitely not 0. This is equal to k times minus 2y in the x direction. We're keeping the k out the front, minus 3z in the y direction, minus x in the z direction. So that is not equal to 0, so not electrostatic field. Now, we should check B as well, make sure that the curl of the electric field given in B is 0. So we'll go about this the same way. We've got x, y, and z, and we've got d dx, d dy, d dz, and then we've got y squared, we've got 2xy plus z squared, and then we've got 2yz. And so this is equal to k, and in the x direction, we've got d dy of 2yz. So that is going to be 2z. And then we've got d dz of 2xy, which is 0, plus z squared, which is 2z. So that's minus because we subtract off d dz of this thing. And then in the y direction, we've got d dz of y squared, so that's 0, minus d dx of 2yz, so that's also 0. And then in the z direction, we've got d dx of 2xy, so that will be 2y, and d dx of z squared, which is 0, and then minus d dy of y squared, which is 2y. And so you can see this thing here is going to be equal to 0, and this is 0, and this one here is obviously 0. So in this case, this does equal 0, so it is a possible electrostatic field. Okay, now let's move on to the second part of the question. In the second part of the question, it says, for the possible one, find the potential using the origin as your reference point. So what we want to find now is V, and we know that E is equal to minus grad V. And so we're going to need to integrate our electric field in order to find out what the potential is. And in order to integrate it, we are going to have to come up with some path to do that over. So let's sketch a little diagram over here. We've got X and Y and Z. And the question told us to use the origin as our reference point. So we're starting here at 0, 0, 0. And we're going to any random point. Let's call this x0, y0, z0. And we're going to have to do this integral over a path. So let's take the simplest possible path. Let's go in the x direction. So we'll go from 0 to x 0, 0, 0. And then we'll go in the y direction. So this is to x0, y0, 0. And then we'll go up in the z direction to x0, y0, z0. Okay, so let's call this one here part 1. Here we've got part 2, and here we've got part 3. And we'll integrate for each of those parts. So part 1, we've got x is going to x0, y remains at 0, z remains at 0, and we've got dl. In this case, is just going to be equal to dx 0, 0, because we're not taking any increments in the y or the z direction. So what we care about is the integral here from 0, 0, 0 to x0, 0, 0. And we're doing e dot dl, and so in this case we only really need to worry about the dx component because dy and dz are 0. So I'm going to save myself some time and only consider my x part. So this will be y squared dx, and again the y and the z are 0. So let's go from 0 to x0, and when I do this integral here, I end up with y squared x naught. I left off my k here, so let's put that back in. So it should be ky squared x naught. But along this path, everywhere y equals 0. So this is 0 along this path. Okay, so we've done that first part. Now we want to do this second part. So now we are going from x naught 0, 0 to x naught y naught 0 and e dot dl again. But along this second part here, we've got that dx here, dx is equal to 0 and dz is equal to 0. It's only dy which is going to contribute. So in this case, we can write that this is x0, 0, 0 to x0, y0, 0. And we've got k times 2xy plus z squared dy. And so this is equal to k times, what will this be, xy squared plus z squared y. And then we'll need to consider these limits on the integral. So everywhere we've got x0, x is equal to x0, that's in both the top and the bottom, and we've got z is equal to 0 in both places. So because there's a z in both terms, this term is always going to be 0. This term here is always going to be x naught, and y is going from 0 to y squared. And so when we evaluate this, this is going to be equal to kx naught times y naught squared. And so that's along path 2. And now we finally have to do path 3. So now we're going from x naught, y naught, 0 up to x naught, y naught, z naught. And that's of E dot dl. And along this path, we've got dz is not 0, but dx and dy are 0 because they're not changing. So this will be from x naught, y naught, 0 to x naught, y naught, z naught. And this will be of 2yz dz. And so doing, with my k, I forgot my k again. So this will be equal to, what is it, kyz squared. And x will always be x naught, it's not changing. Y will always be y naught. And z is going from 0 to z naught. And so this is equal to ky naught z naught squared. And so summing these up, because we need to sum the integral over all these different paths, gives us that the integral of the electric field, which is equal to negative the potential kx naught y naught squared plus ky naught z naught squared. And so we can write, this tells us that V is equal to minus K xy squared plus yz squared. And now let's just check that we've done this correctly. What we'll want to do is differentiate V, because we've got, remember that E is equal to minus grad V. Let's work out what minus grad V is and check that we get this expression for E back. So we've got this, in this case, is equal to minus d dx of xy squared plus yz squared. When we do this part, we just end up with y squared in that x direction, so that is right. And then in the y direction, we've got d dy of xy squared plus yz squared. And so differentiating this with respect to y, we're going to get 2y times x, which is what we get. And then when we differentiate this second part, we're going to end up with plus z squared, which is what we get. And then finally, we've got d dz of x squared plus xy squared plus yz squared. When we differentiate that with respect to x, this first term gives us 0, and then this second term gives us 2yz, which is what we get there. And I left my k off again, so that was all times k. And so this is our expression here for the potential for the electric field given in B. Okay, so let's have a bit of a discussion about potential. I'm hoping that you remember most of this stuff from Physics 1B, where you first learnt about electrical potentials. Okay, so first of all, the name potential is not the same thing as potential energy. It is related, but it's really not the same thing. So we'll come to how it's related later. Now, the advantages with using potential rather than electric field is that the potential is a scalar. So we're just dealing with the one component in this case. So often problems are much simpler to solve if we can solve them for the potential and then use the potential to get the electric field if we needed the electric field, rather than working through everything with the vectors. So that's an advantage of using the potential rather than the electric field. Now, it's important that we define our reference point. Generally, we take the point with zero potential at an infinite distance from the source. And we can then define what the potential is at each point relative to that point an infinite distance away. This is what we usually, however, not in every single case, because sometimes this just doesn't work. So for example, if we have a charge distribution that extends out to infinity, then this isn't going to work. It's going to blow up. So then we need to choose somewhere else which is sensible for that problem. So it's just really careful that when you're solving problems with potential, that you think carefully about where your 0 point is. Now, potentials obey the law of superposition. That's because we've said forces obey the law of superposition. We're talking about electrostatic here. So electrostatic forces obey the law of superposition. The electric field is related to the force because we just divide it by that test charge to get the electric field. And then the voltage is related to that electric field because the electric field is equal to minus that triangle's a bit funny, of the potential. And so to get the potential, we just need to integrate the electric field. So if electric fields obey the law of superposition, then it follows that voltages must also obey the law of superposition. So the units for potential are Newton meters per coulomb, which makes sense because to get from the force, which is newtons, to the electric field, we divide it by the coulombs. And then to get the electric potential, we're integrating and it's over this distance vector here. So we're multiplying that by meters. And we can also write this as joules per coulomb, or it's got its own unit called the volt. Okay, so let's do an example problem now. We're asked to find the potential inside and outside a spherical shell of radius capital R, which carries a uniform surface charge density sigma, and we're told to set the reference point at infinity. Okay, so that means that the voltage is equal to 0 at this point, which is an infinite distance away from the center of this sphere here. So let's start with, not inside, we'll start with outside because that's going to be a little bit easier to calculate because we're on the same side of the sphere as our reference point. So let's consider a spherical Gaussian surface with radius little r like this. This is little r here, and we've got that r is greater than big R, and that's what we need to be outside this sphere. So we can use Gauss's law, and Gauss's law tells us that the integral of the electric field times dA, so the flux through this closed spherical surface, is equal to the enclosed charge divided by epsilon naught. And now all the enclosed charge is at this radius capital R here. And in the question, we're given the surface charge density. So the amount of enclosed charge is going to be equal to that surface area, which is 4 pi r squared, times the charge density divided by epsilon naught. And we're considering the flux through this area. But in order to get the potential, because we've got our equation that the electric field is equal to minus the gradient of the voltage or the potential, we're going to want to find our electric field in order to get our potential. So we're doing this to get our electric field. So because there's the dot product here, we know that the electric field and our area are going to be only the parallel components will count, and so this is pointing directly out of this sphere here. So we can write, well, the electric field times the surface area, which is going to be 4 pi little r squared. Notice that this is little r squared because it's the surface area where we're finding the electric field, is going to be equal to 4 pi big R squared, because that was related to the actual amount of charge, which was the area of our sphere there. And so these will cancel out, and we have that our electric field is equal to r squared sigma over epsilon naught little r squared. And this is a vector, so we should have a direction, and we've said that that is in the radial direction there. So now we have an expression for the electric field, and now what we need to do is find the potential. So because the electric field is the derivative of the potential, to get the potential, we're going to have to integrate the electric field. So this is going to be equal to minus the integral from our origin point, which is our reference point is at infinity. So this is going to be our point at infinity. We'll call it P here, and R and E dot dl. And now let's substitute in what we know for these. We know that P is at infinity. Now we're going from infinity here to point R here. E, we've just worked out above, that's r squared sigma over epsilon naught r squared, and then it's dr, because it's only the radial component that we've got an electric field for. And just to be strictly correct, this r here is this point here. These r's are varying because they're all along this path here. So technically they're different things. So let's put a little prime there and a little prime there. Inside they're the same, but it's different to what this thing is, because this is now a point. So we can solve this. We've got minus r squared sigma over epsilon naught, and then we're doing the integral of 1 over r prime squared dr prime. So when we do that integral, we end up with minus 1 over r prime, and that's from infinity to r. And so this is equal to r squared sigma over epsilon naught. I'm just getting rid of my negative because there's two of them. And then this is 1 over r minus 1 over infinity. And 1 divided by infinity, that's 0. So this is equal to r squared sigma over epsilon naught r. So we've now got an expression for the potential outside our sphere of charge there. So now let's work out an expression for the potential inside. So now we're going to want a Gaussian surface like this one, which is at radius r here. And for the green one, we've got r is less than r. And in this case, inside here, we have no enclosed charge. So inside, Q enclosed equals 0, which tells us that the electric field is equal to 0. Okay, so what we're going to need to do to get the potential here is we do actually have to do, we'll have to do this same integral here, but we're now doing it all along the path. So we're doing it to here, and then we're doing it to here. And it's important that we distinguish between those two, because outside in this first part, I'll label that R1, there is an electric field there. So we can't simply say that's 0 because it's not 0 along that point, but it is 0 inside here. So we're going to want to do both these integrals to make up the entire path. So in this case, we're substituting into this same thing here, but we're splitting the path into the two bits. So let's go from P to capital R. So we've got minus the integral from P is at infinity. We're going to radius R, and then that's r squared sigma over epsilon naught r squared dr. Because I've got capital R, well, let's put the primes. We'll just keep it consistent. And then I'm going from r here to little r here. So minus from r to little r. And this is 0 in this case because the electric field inside there is 0. Okay, so this whole part is 0. And this thing here we can integrate. So we integrate that exactly the same way. This is minus r squared sigma over epsilon naught. And now we've got minus 1 on r prime. And this, in this case, is going from infinity to capital R. So this is equal to r squared sigma over epsilon naught times 1 on r minus 1 on infinity. And that's just 0 again. And so this is equal to r sigma over epsilon naught. Okay, so this brings us to Poisson's equation. So we've seen that the relationship between the electric field, which is a vector, and the potential is given by E is equal negative the gradient of V. We've also seen Gauss's law. This is Gauss's law in the differential form, which tells us that div E is equal to rho over epsilon naught, where rho is the volume charge density. And we've seen that electric fields must be curless. So the gradient of E is equal to 0. Okay, so what we can do now is put these equations together to get Poisson's law. So we are going to start with this one here. We've got that the divergence of E is equal to the divergence of, in this case, because the electric field is equal to the gradient of V, well, negative the gradient of V, we can replace E here. Sorry, that should have been a vector. Let's put a line underneath that to make that really clear. Is the negative the gradient of V. So that's what I've done there. I've just used this equation up the top to replace that. And so we've got that the Laplacian of V, that's grad squared V, is equal to the divergence of E, but we know that the divergence of E is rho on epsilon naught. So we can rewrite this line here this way, where we've shown that the Laplacian of V, which is Nabla squared of V, is equal to minus rho over epsilon naught. And this is known as Poisson's equation. So what we're going to consider now is how we can calculate the potential of a localized charge distribution. So in order to do this, we're going to start with the simplest case, just for a point charge, like I've sketched right here. And just remember that we've said lots of times that the electric field for a point charge is given by 1 over 4 pi epsilon naught q, that's the size of the charge, divided by r squared times r hat. So this gives the direction that's in a radial direction. And when we introduced potential, we said that because the potential and the electric field are related through the electric field is equal to minus the gradient of the potential. To get the potential, we need to integrate the electric field, and we do that integral from the point where the potential is 0. So we usually take this at infinity. So Griffiths writes this as a curly O to the point R, and it's E dot dl, where E is the electric field there. So let's start by calculating the potential for this point charge here. We'll want to substitute our electric field here into this equation here, and the electric field for a point charge is only in the radial direction. So when we're considering dl, we only have to take that radial component, which is just dr. So we can write, well, in that case, vr is equal to minus, and we've got the integral. We're going from infinity because in this case the potential is 0 at infinity to r, and then it's 1 over 4 pi epsilon naught q divided by r squared, and then that's times dr, because both these are in that radial direction. They're in the same direction. And we probably better just be a bit proper here. This r and these r's are different things. So these r's inside are the same thing. So let's put a prime, but this r is the end point. These r's range over our entire path from infinity to the point r. Okay, so let's do this integral. We can write this as minus q over 4 pi epsilon naught. I'm just pulling all the constants out the front. And then we're going to do the integral of 1 over r squared dr. So that's minus 1 over r. And this is from infinity to r. And so this is equal to q over 4 pi epsilon naught times, because those negatives cancel out, we've got 1 over r minus 1 over infinity, and 1 over infinity is 0. So this is equal to q over 4 pi epsilon naught r. And so now we have an equation for the potential of a single point charge, a distance r from that point charge, as long as we can assume that the potential is 0 at infinity. So if v equals 0 at infinity, then we have that v of r is equal to q over 4 pi epsilon naught r for a single point charge. But we don't always just have a single point charge. Sometimes we have a whole charge distribution. So let's now expand this a little bit and assume that we've got lots of point charges here. Let's say that we've got qi from I equals 1 up to n point charges, and we want to know, well, at some point p here, what's the voltage given by all of those point charges? Well, we've already shown that potential obeys the law of superposition. So all we need to do is sum these up for all these charges. Now, remember that r is the distance from our point P to the point that we're considering. So that is going to be different for each of those charges. So we can write in this case, V of r is going to be equal to 1 over 4 pi epsilon naught. Now, each charge has its own amount of charge and also its own position. So its position is given by Ri. The charge at position Ri is Qi, and this is from I equals 1 to n. And so that gives us a way to calculate the potential for a series of discrete charges. But then sometimes we have a big continuous charge distribution as well. So like maybe we have a rod here or something, and we want to work out, well, what's the potential over here due to this rod? Well, in that case, we'll need to break it up into lots of little discrete bits and integrate rather than sum. So for a continuous charge distribution, we're going to have V of r has a similar expression, but now it's 1 over 4 pi epsilon naught, and now we're doing the integral of 1 over r dq. We're summing up all over all those little charges. Okay, and just remembering that dq is the charge located at this location here. So when we have a volume charge distribution, rather than, we can use dq, but the amount of charge at this position is given by the charge density at this position times the volume, the volume of that position there. So we can also write this as 1 over 4 pi epsilon naught times the integral of 1 over r times rho r dv. I'm using dv, whereas Griffiths uses d tau, but they're the same thing. This is a little increment of volume. So this gives us an equation for how we can calculate the voltage if we know the distribution of the charges. So we'll see how to do that very shortly. Just to point out, this is very useful because there's no vectors here. This just has a single component, and so while it can occasionally be a bit challenging to calculate, it's much simpler than if we considered the equivalent expression for an electric field. For an electric field, because this is a vector, we've got that the electric field is equal to 1 over 4 pi epsilon naught times the integral of rho of r over r squared times r hat dv. So in this case, the r hat makes these much harder to deal with. And this is our expression for a volume charge distribution. Of course, like the one I've drawn here looks possibly more like a linear charge distribution. We've got, for a linear charge distribution, we can write V of r is equal to 1 over 4 pi epsilon naught times the integral of lambda of r over r dl in this case, because it's linear. Or if we had a surface charge distribution, we could write as 1 over 4 pi epsilon naught times the integral of sigma of r divided by r dA in this case. But I think it'll become clearer how to do this if we do an example problem now. So now what we're going to see is how we can use this technique to solve the same example problem as we solved previously. So in this problem, we're asked to find the potential V, a distance Z above the center of a uniformly charged spherical shell of radius r and surface charge density sigma. So this is the one that we solved back here, but now we're going to use this different technique to solve this. Okay, so in order to use this technique, let's sketch a little diagram showing what we're doing. So here is our spherical shell. Let's draw on our axes. Here we've got X, here we've got Y, and here we've got Z. And we're considering a point P up here, which is a distance Z above the spherical shell. And what we'll do is we'll consider a little part of the surface here. So this has got our area, dA prime is the area of this, and it is at a radius r from the center. And this angle in here is equal to theta. And we can draw this line here. And the distance from this little increment to our point P is this curly r. That's this curly r here. So considering this diagram, let's write down what we know to substitute into this expression here. So we know that our curly r thing here, which is this side here, we can use the cosine rule for that, because this isn't a right angle triangle, but we've got the angle theta in here. We've got that this is r, we've got that this is z, and this is our curly r. So our curly r squared is going to be equal to r squared plus z squared minus 2rz cos theta, just from our cosine rule, a squared equals b squared plus c squared minus 2bc cos a. And we also know that our surface area, dA is going to be, I'm just going to drop the prime because I'm a little bit lazy. But yeah, this is talking about the surface area of this little bit here. This is given by r squared sine theta d theta d phi, because everything's at the same radius, so we're integrating over d theta and d phi to get the surface area in this case. So let's write out fully what we mean by this integral here, and we'll also make these substitutions into it. Okay, so in this case, we're trying to find how it varies as z varies, a distance z above. So our potential is a function of z, and this is equal to 1 over 4 pi epsilon naught. And then because we've got the dA there, what we mean by this integral sign is that we're doing a double integral. So we're integrating over phi and over theta. So let's draw our double integral. Now, sigma in this case is not a function of the radius or the angle, because we're told that it has got a uniform charge density. So that's just a constant, sigma. And then we've got on the bottom our curly r, which is here the square root of r squared plus z squared minus 2rz cos theta. And then we have to substitute in our dA, which is r squared sine theta, and this is d theta d phi. And now what we should do is consider the limits of our integral. So theta, this goes from 0 degrees, which is parallel to the z-axis, down to here, so that's pi. So we're going from 0 to pi. And phi goes all around the circle like that. So that's from 0 to 2 pi. Okay, so let's simplify this as much as we can. If we can get rid of this fraction just by writing this is 4 pi epsilon naught, the voltage is a function of z, just to get rid of this down the bottom. Now you can see that nothing inside our integral here is an integral of d phi. So when we integrate from 0 to 2 phi, we're just integrating a constant. And so that's going to be 2 pi times whatever that constant is. So I'm going to write this as 2 pi. And that's getting rid of this integral here, which I've underlined in red. So that goes to that. And now I'll pull my constants out the front of the integral. So I've got sigma r squared. And now we've got the integral from 0 to pi of sine theta divided by the square root of r squared plus z squared minus 2rz cos theta, and that's d theta. Now what I can do is I can cancel that pi with that pi, and I can cancel that 2 with that there. Okay, now this part here is just a standard integral. So let's substitute in the value for that on the next line. So we've got 2 epsilon naught, the potential as a function of z, is equal to sigma r squared. And then this standard integral here is equal to 1 over rz times the square root of r squared plus z squared minus 2rz cos theta. And that's going from 0 to pi. And so now what we can do is substitute in our limits. Oh, but first there's a little bit of simplification. We can get rid of that r there. And so let's just write this as Vz is equal to sigma r, and I'm just going to divide by this now, and I'll pull the z out the front, and then I've got, when I put pi into cos theta is equal to -1. So this is the square root of r squared plus z squared minus, well, plus 2rz, because it's minus minus 1, minus the square root of r squared plus z squared. When I put 0 into cos theta, I get 1. So this is minus 2rz. Now, hopefully you can see that in here, this is just r plus z squared. And in here, we've got r minus z squared. So this is equal to sigma r over 2 epsilon naught z. And we've got the square root of r plus z squared minus the square root of r minus z squared. Now, at this point, it's important to think physically about our setup. In our setup, we said that z was a distance above the center of the sphere. So physically, as z is above, we've got that z is greater than r. And if z is greater than r, this tells us that the square root of r minus z squared is equal to z minus r, because z is bigger than r and we want this thing to be, well, it has to be a positive number. So you just need to be very careful with that. You can't just use the square root to get rid of the square, because when we square something, it could be positive or negative. So we have to think about, well, how do we meet that condition in this case? Okay, so now we can substitute that in, and we've got that v of z is equal to sigma r over 2 epsilon naught z, and we've got the square root of r plus z squared is r plus z, and then minus, and we've said that this thing is z minus r, so minus z plus r in this case. So this is going, those z's will cancel out, and this will be equal to sigma r over 2 epsilon naught z times 2r. Those 2's will cancel, and I'll end up with sigma r squared over epsilon naught z. Okay, so we did solve this problem another way, so we should have ended up with the same result. So let's just have a look back and see if that's true. Here is our result from when we solved it this time, r squared sigma epsilon naught r, and for this problem, r was the distance from the center of the sphere, which is the same as z in this case. So those two are in agreement. Let's just to really check our working, calculate for the one that we've currently done what happens if we take z inside the sphere, and in that case we should get r sigma epsilon naught. So let's just check that we can get that back as well. Okay, so we were hoping to get r sigma epsilon naught inside. Okay, so inside we've got that z is less than r, and so this tells us that the square root of r minus z squared is equal to r minus z. And so in that case, we've got that v of z is equal to sigma r over 2 epsilon naught z. We've got r plus z minus r plus z. So in that case, the r's cancel out, and we've got sigma r times 2z divided by 2 epsilon naught z, and the z's will cancel out, the 2's will cancel out, and we end up with sigma r over epsilon naught, which was what we got last time. And so that is another way that we can solve this problem. In this case, we didn't need to know about the electric field. In the previous case, we needed to use what we knew about the electric field in order to calculate the potential. So far we've mainly been looking at rho, which is the volume charge density, E, the electric field, and V, the potential. So let's now just summarize how these are related to each other, and then we're going to look at the boundary conditions that apply. So Griffiths has a really useful triangle for relating these three quantities. So let's just discuss how if we've got one, we can calculate the other. So say we have rho, the volume charge density, and we want to calculate the electric field. Well, in that case, we're going to need to use our version of Coulomb's law. So we know that the electric field, which remember is a vector, so we need to calculate this in all three dimensions, be they spherical components or Cartesian components, or we could do it in polar as well. And this is equal to 1 over 4 pi epsilon naught. And then we need to integrate, and it's 1 over curly r squared, where this is the distance between the charge and the place where we're measuring the electric field, times the volume charge density. And now it's in the direction pointing from the charge to the place where we're measuring the field. So this is our unit vector in that direction, and then times dv, or Griffiths uses d tau for this, but this is the volume increment. So it is quite involved because we have got this vector here if we want to calculate the electric field given the charge density, but you've seen a few examples of how that can be done. Now, it's a bit simpler if we want to calculate just the potential, because the potential is a scalar. So this is given by 1 over 4 pi epsilon naught. And then it's very similar, except that this is the charge density divided by that curly r, which is the distance between the point charge and the place where we're measuring the voltage, times dv. So this does not have that vector in it, so it's an easier integral to do. And then if we want to go back the other way, it's a little bit simpler, because it's usually simpler to take a derivative rather than calculating the integral. So if we want to get from the potential to the charge density, we can just use the Laplacian in this case. So the Laplacian of the potential is equal to minus rho over epsilon naught. And if we have the electric field and we want to get our charge density, then there's a couple of equations that have to hold. So remember, electric fields can't be given by anything. They have to be curlless. So we've got that the curl is equal to 0. And then to get the actual value, we're going to need to use the divergence. So del dot E is equal to rho over epsilon naught is how we can calculate rho, the charge density, if we know what the electric field is. And these electric fields are, of course, vectors. And then if we want to get between the voltage and the electric field, well, it's relatively easy getting from the electric field to, from the voltage to the electric field, because again, that's taking a derivative. So the electric field is equal to minus grad V, which will give us a vector because we differentiate in each direction. And then if we want to get from the electric field to the voltage, that's a little bit more complicated because we need to do an integral, and it's equal to the integral of the electric field over the path. So that would be how we'd calculate the voltage in that case. Okay, so now we're just going to have a bit of a discussion about boundary conditions, because if we don't account for these properly, we can end up with stuff blowing up. So it's just really important that we think about where we have to account for these boundary conditions. So just to give you an example, where we saw this before was in this problem here, where we were considering we had to calculate the potential, and we worked out the electric field, but the electric field wasn't a continuous function between the inside of the spherical sphere and the outside. Inside the spherical sphere, we had zero electric field. So that's where this part of our integral came from. That was the electric field inside. Whereas outside, the electric field was given by this r squared theta epsilon naught on little r squared, which you can see these two don't match up. The electric field isn't zero just before we go inside this sphere of charge here. So that is a discontinuity, and we had to account for that and split this integral up into the two parts so that we weren't like just treating it naively and doing something stupid. So that's why we need to think about what happens with these boundary conditions. So in order to do this, let's consider just a big plane of charge, surface charge density sigma, and then we are going to consider a little box like this, sometimes referred to as a pillbox. It's referred to as a pillbox in Griffiths, and we'll let it have a height epsilon naught with half of that up above the plane and half of it down below the plane, and we'll consider the surface area of the box that we're considering equal to A. Now, if we consider this Gaussian surface here, which is the surface over our entire box here, with these sides that are perpendicular to the plane, they're going to be parallel to the electric field. And so that is not going to contribute to the flux. So we're going to be using Gauss's law to consider the flux here. So remember, Gauss's law tells us that the integral of the electric field over our Gaussian surface is equal to, well, that is the electric flux, and it is equal to the enclosed charge divided by epsilon naught. And for a box like this, the enclosed charge is given by sigma A, so that's equal to sigma A over epsilon naught. So this should be familiar from physics 1B. Okay, so we can write this as E above and just perpendicular to the surface. So that's this part here times A minus E below perpendicular. So remember, we're not at this point assuming the direction for the electric field. We're kind of in the process of showing that it's discontinuous. So what we actually know is that above it's like this and below it's like that, which is why it is discontinuous. But at the moment, we're in the process of showing that this is the case and that this is discontinuous. So A there is equal to sigma A over epsilon naught. So these A's cancel out, and we've got that E above perpendicular to the plane minus E below. So that's the electric field down here. It's talking about the electric field through this surface here. Perpendicular to the plane is equal to sigma over epsilon naught. And then if we consider letting this epsilon go to 0, so this thickness go to 0, you can see that it remains at this. So that is telling us that there's a discontinuity, because as these two approach each other, if it was continuous, they'd approach the same value, but they don't. They approach sigma epsilon naught. So this implies it is discontinuous. It being the electric field perpendicular to this plane, so the i.e. normal component of E. So when we pass through a plane of charge, then the electric field is discontinuous, normal to that plane. Now, if we consider the tangential component of the electric field, we're going to want to use a slightly kind of different shape there. So let's take a rectangle like this. It's going below. So now we're considering going around a rectangle like this. And so we're now considering the electric field this way. And we can write in this case, well, E dot dl, you may remember that equals 0 because of the curl. I mean, it has to be 0 because we know that the electric field is curlless. And so Stokes' theorem tells us, and remember this thing's just dA. It's the same thing as what we had as dA up here. So this thing here has to be equal to 0, and so we've got that this thing round here has to be equal to 0, and so this tells us that here they're going the electric field and the line are going in the same direction, whereas down here the electric field and the line are going in the opposite directions. So this tells us, if we want to write it out in full, that E above parallel times L minus E below parallel times L is equal to 0, which tells us that E above is equal to E below. And so this tells us that parallel to the plane, the electric field is continuous. So parallel to the plane of charge, E is continuous, which means that combining these two, because now we've got a perpendicular and a parallel component, we've got that E above minus E below. We only have the perpendicular contribution, and so that's sigma over epsilon naught, and that's in the normal direction. So if you are working out electric fields around a plane of charge, just remember that you do need to account for this discontinuity. Now, if we consider the voltage, let's switch to purple so that we don't end up getting confused. Let's consider the voltage from a point above. Let's call that B to a point below. And if we know that the voltage is related to the electric field through the voltage is equal to minus the integral from A to B of E dl. And so this tells us that V above minus V below is equal to minus the integral from A to B of E dot dl. And we know that as A goes to B, i.e. as these two get really close, so our path length goes to 0, then this integral has to go to 0 as well. So as A goes to B, the integral from A to B of E dot dl goes to 0. So that tells us that V above is equal to V below, which tells us that the potential is continuous. So that makes the potential easier to deal with there than the electric field. But because our potential is, the integral of the electric field, we can say the easiest way to write this is that the electric field is equal to the gradient of the potential, and the electric field is not continuous. So this tells us that the gradient of the potential is not continuous. So using this equation here with, this equation here, this E is the same as this E. So we have got that the gradient of the potential is negative this thing. So that's minus sigma epsilon naught in the normal direction. And so this tells us that the gradient of the potential is not continuous. So gradient of potential is not continuous. So the moral of the story is just be very careful when you've got sheets of charge about what's happening at the boundaries there, because the electric field is not continuous, so you do need to account for that in your calculations.